Okay, this is a tricky organic analysis NMR one. So let's go. Question 6: compounds V, W, X, and Y are isomers with the molecular formula C5H10O2. Isomers V and W are carboxylic acids with formulas that can be written as C4H9COOH. Give an equation for the reaction C4H9COOH with sodium hydrogen carbonate. Pause the video, have a go. You know this one, easy peasy. You're just looking at a carbonate with an acid, right? Essentially. And what do you make if you do carbonate and acid? You know this from GCSE chemistry. You're going to make salt, carbon dioxide, and water. So the salt here, we've got like, I don't know, we don't even know what structure it has, but butanoate. So it's going to be like sodium butanoate, essentially. You don't need to put the minus and the plus. I'll probably get rid of that. Plus water, plus CO2. Yeah, let's get rid of that minus and plus. Normally on mark schemes, they accept that, but, best not to. There we go. So let's go to 6.2. An isometric, isomer V. So one of the two carboxylic acids, because we're told they're V and W. So the first carboxylic acid V has an asymmetric carbon atom. Deduce the structure of V. So what we want to do here is pause the video, grab your pen, grab a scrap bit of paper, see if you can work out what structure V is. Now remember that chiral carbons are ones that, or asymmetric carbons, that's just another name for a chiral carbon. They have 4 different groups attached. So play around with the structure. We know the molecular formula is C4H9COOH. Play around until you can find a carbon that has 4 different groups attached. Get that practice in, make it active. All right. Let's go through the answers. There's no point in just watching me go through the answers. You need to play around yourself and get used to it. So here is our straightforward, whatever that is, pentanoic acid. Now you can see there, that can't be chiral. Why? I've put a star next to that carbon. It's got 2 hydrogens attached, right? So all I'm going to do is take a methyl group. So that's how I would start. I would start by drawing that out and then look what I've got to do. Take a methyl group and attach that to that carbon there. And now what you're going to see is I've got an ethyl group here. I'm just putting the hydrogens on. So now we've got this ethyl group. There we go. Oh God, I'm going to delete this. It's all a bit close and club. Right. There's nothing wrong with it, but it's just visually hard to see what I'm talking about. So what I've done is I've moved the first carbon down and stuck it coming off the carbon number 2, or the 5th carbon, sorry, and attached it to carbon number 2. Carbon 1 will always be the one with the carboxylic acid. It takes priority. So we've got an ethyl group, a methyl group, a hydrogen atom, and a carboxylic acid group. That is a chiral carbon, asymmetric, carbon atom, isomer V. Now we're going on to 6.3. Isomer W, which is the other carboxylic acid, has 4 peaks in its H1 NMR spectrum. So it has 4 peaks show up. Deduce the structure of isomer W. We know it's a carboxylic acid. Deduce the integration ratio for the 4 peaks in the H1 NMR spectrum of W. It's worth 2 marks. Grab your pen. I think this is particularly tricky. I'm going to go through the answer, so don't beat yourself up. But again, you're just trying to rearrange the structure. It can't have the same structure as the V, the one we just did. What was that? 2-methyl butanoic acid. It can't have the same structure as 2-methyl butanoic acid, but it's got to have the same molecular formula. So just rearrange it a little, because we still know it's a carboxylic acid, and try and work out the structure. Deduce the integration ratio for the 4 peaks. Let's go. Okay, so if we look at the previous question, we did isomer V. We know this is just an isomer of isomer V, so I can't put the methyl group there on the first. I could try butanoic acid. That's not going to work. I kind of, we need 4. What does it tell us here? Oh my gosh, it's got 4 different peaks. So I need 4 different hydrogen environments, 4 different hydrogen environments. One of those hydrogen environments, let's do it. And we've got to write down the integration ratio and the structure. So I'm going to try this structure. I've just moved the methyl group 1 over. And look, we've got 2 methyl groups there, same hydrogen environment. I've got, so that means I'm going to have an integration trace of 6 for that hydrogen environment, because they're both identical environments. Now I've got this, which is a unique environment, a CH, and that's going to go, it's got 1 hydrogen, so it's going to have an integration ratio of 1. The OH is going to have an integration ratio of 1, and then I have this CH2 group here, which is another hydrogen environment, and that has an integration ratio of 2. So I would get 4 peaks here. And there we go. It would be 6, 1, 1, 2. And there we go. 2 marks. Lovely. Right, 6.4. Isomer X has three singlets with an integration ratio of 136 in its H1 NMR spectrum to deduce the structure of X. This no longer has to be a carboxylic acid, and it definitely won't be a carboxylic acid. So we need to get that molecular formula down. It won't be a carboxylic acid because it told us W and V were, but it has the same molecular formula, so C5H10O2. So I definitely need to write down the molecular formula, and I need to rearrange the structure so that it has three singlets, so three hydrogen environments that produce singlets, which with a ratio of 136 in the HNMR 1 spectrum. Explain why the peaks uh, in the spectrum are singlets. Now, there's a whole bunch of ways. What can I do with these O's? We know it's not carboxylic acid, so I could have carbonyl group COO bonds. I could have OH bonds coming off. I could do some sort of ester link where you have like an oxygen atom in the middle. So let's have a little look. The integration value of 6 makes me think it's CH3 times 2. But then I know it mustn't have any hydrogens on the adjacent carbon, right? Because they're telling me that all the peaks produce a singlet, all the poops. So I know that here, this would have an integration ratio of 6, the CH3 and the CH3, but that carbon cannot have a hydrogen on it. So I don't know, I'm going to stick an oxygen coming off of it and a carbon coming off of it. I could have, as long as I don't have another hydrogen coming off, that would produce a singlet, because a singlet tells you there's no hydrogen on the adjacent carbon. So let's just try and get all the I'm going to put there must be loads of compounds you could do with this. I'm going to get a carbonyl group there. Let's put a carbon there. I just need to make sure I've got all with the molecular formula. Okay. Yes. Let's see. I would get, you see, I've got this methyl group here. That is an integration ratio of 3. So this one on the right hand side has an I for integration of 3. It's a singlet because the carbon next to it, I've stuck a carbonyl, I've stuck the COO bond, so there's no hydrogen on that. That's why it's a singlet. And then this hydrogen atom on the OH would produce a singlet as well, because the H has no atom next to it with a hydrogen attached. It's got an oxygen actually, not even a carbon. So that this formula, this structural formula or display formula would give me 3 peaks in a ratio of 136. So this is my viable answer for the marks. I have to say, it's a tricky question. Don't slap yourself in the face if you found this really hard to do. This NMR takes practice, 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 practice for you to get excellent at it. It's a skill-based topic, not a memory recall topic. 6.5, Table 2 shows the information about the peaks in the H1 NMR spectrum of isomer Y, chemical shift 3.65 and 1.19, integration ratio 2 and 3. We've got splitting pattern, singlet, singlet. Draw the parts of structure Y that can be deduced from each of these peaks, deduce the structure of Y, and then state how many peaks in the C13 NMR spectrum of Y, and it's 6 marks. Boom! Pause the video, have a go. Right, I'm going to go through the answer here. So you've got to bust out your data sheet and you've got to look up 365, and you're going to get your first marks on the board by just looking up, look, 3.1 to 3.9 chemical shift. It has to be ROCH. Now, it can't have the chlorine or bromine attached, which is 3.1 to 4.2, because there's no bromine or chlorine in our molecular formula. So always check what's in your molecular formula. Now let's look at 1.19. That goes 1.19. Oh, check it here, 0.7 to 1.2. It's going to be a CH3 group. So we now know, and you're going to get 2 marks out of 6 for this, for saying the 1.19 is a CH3 group and 3.65 is the RO group. So let's get this down. The molecular formula, remember, is C5H10O2. I'm going to go through the answer. So the 3.65 told us that it had to be the RO group, which we could see from our chemical shift data. Now, the fact that it had an integration ratio of 2, and that is 1H, tells me that there's going to be 2 of these O groups. More than likely, I'm going to end up with 2 of them because the integration ratio was 2. Now, why does that mean I'm going to end up with 2 of these bad boys? We'll come on to that. The total integration ratio is 2 and 3, which is 5, and that is half the amount of hydrogens. So actually, each one of them has probably got 2 hydrogens attached. And so you're going to attach those together because it's one environment with an integration trace of 2. You might say, how do I know that 2 is 4 hydrogens? Well, the total integration ratio is 5, 2 plus 3, and there's 10 hydrogens. I'll explain a bit more about that in a second. So I'm going to do 2 of those RO groups where the R bit is CH2, and I'm going to join them together to make one environment, one peak, like that. Now, 1.19, we're going to go with it CH3, isn't it? We worked out that the chemical shift was CH3. You'll get 1 mark for that, for identifying 1.19 as CH3. Now what I need to do again is look at this integration ratio. Remember, the integration ratio is 3 and 2, which is 5. The total integration ratio is 5, but we have 10 hydrogens with an integration ratio of 5. So each integration ratio point unit, there's 5 units there, each unit is worth 2 hydrogens. So 10 divided by 5 is 2. So as the integration ratio is 3, this means I've got 3 times 2. I must have 6 hydrogens in this hydrogen environment. Okay, so there's 6 hydrogens in this hydrogen environment. If the chemical shift is CH3, I've got 2 CH3 groups. So I've essentially worked out all my stuff. I've got 2 CH2s because of the integration ratio of 2. And then I've got 2 CH3 groups because that has 6 hydrogens, and we worked out 2 hydrogens per integration ratio point because there's a total of 5. So these 2 CH3 groups must be connected because they're part of the same hydrogen environment. So I need to connect all of this stuff up. So what I'm going to do here, I know I need a 5th carbon because I've got 5 carbons. So I've got 2 CH3s, 2 CH2Os, and I'm going to have to stick a random carbon in the middle here. Now, there might be more than one structure, but this is a viable structure. So there might be more than one structure. You'd have to check the mark scheme. I'll put the link in the description to the exam paper where you can scroll through to question 6 and check the mark scheme on this one. But I'm going to connect my 2 CH3 groups like this. Now, why do they give us a singlet? Think about it. They have an integration ratio of 3 because I worked out that each integration ratio point is worth 2 hydrogens. So 3 times 2, 6 hydrogens. They are connected to a carbon that has no hydrogen on it. So that is why it gives off a singlet. And the reason why the other hydrogen environment gives off a singlet, the ROCH or the CH2O, is because they're connected to the O's, which obviously do not have hydrogens attached. So we've got 2 separate hydrogen environments, one with 6 hydrogens, integration ratio of 3. And then we have this one up the top here. Obviously, they're singlets because they're connected there. But then this one up the top here has 2 CH2 groups, and that's why they have an integration ratio, an I of 2. Each integration ratio point is worth 2 hydrogens here. We can tell that by looking at the molecular formula and working that out. Remember, the integration ratio is the ratio of the number of hydrogens. So the ratio is 2 to 3, because if we just did it as 6 to 4, then you can simplify that down by dividing both by 2 to go to 3 to 2. So it's basically a bit like empirical formula there. And there we go. That is my final molecular structure. And that is going to get me 5 of the marks. So you're going to get 1 for working out the CH3 group is 1.19. 1 for working out the ROCH group is 3.65. 1 more mark for working out the 2 CH3 groups are connected in the same environment. To a carbon with no hydrogen. There we go. That's 2. 1 for working out the 2 CH2O groups are connected, right? And we know they must all be connected because we've only got 2 singlets in the splitting pattern. Oh, I forgot the 6th mark. How many peaks are there? Let me put the formula back up. There we go. Bush. Right. How many peaks in the CNMR? So all you've got to do, how many different carbon environments, not hydrogen, how many different carbon environments are there? So we've talked about the fact that there's only 2 different hydrogen environments, hence the 2 peaks. But how many peaks would you get on a carbon 13? Well, you get those are 1, that one in the middle is unique, and then those 2 are unique. So there's 3 different, so it'd be slightly different than the HNMR. You'd get 3 different CNMR 13 peaks, and that give you the 6th mark. Awesome. Guys, don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.